I'd like to introduce Parker Abercrombie. Parker is the lead developer for basically a suite of applications that encapsulate a very large group of functionality that are generally called OnSight. Parker has a really interesting specialization that crosses visualization, 3D graphics, as well as geographic information systems. Let's hear it for Parker.
Okay, thank you, Scott. Hi, good afternoon. I'm Parker Abercrombie from the Jet Propulsion Lab. And at JPL, I lead a project called OnSight that uses the Microsoft HoloLens to put scientists and engineers virtually on the surface of Mars. So today I'm going to be talking a little bit about the ideas and research that led up to OnSight, some of the capabilities of the system and how it's being used today, and how we've spun this work off into a couple different public outreach and educational offerings. So at JPL, I work in the operations lab. And in the ops lab, we try to take innovative technology and apply it to problems in space exploration. So in the video here, you can see some of our past work, actually some similar things to what Scott showed. And a lot of our focus over the past few years has been in virtual and augmented reality, and especially in head-mounted displays. And what led us to this domain is considering the kind of the plight of our user base, which are geologists who study the planet Mars. So when geologists study Earth, they do this. Like they go out in the field with their colleagues and they walk around and they look at the rocks and they talk about things and form hypotheses and test their assumptions. And when geologists study Mars, they do this. They sit at their desk and they look at pictures of Mars and try to imagine in their head and reconstruct what does that place actually look like if I was actually standing there in the field. And the challenge is that it's easy to look at pictures like this, but it's really hard to do that mapping. So here are some pictures of one area of Mars. This is the Kimberley region of Mars. And these are beautiful pictures to look at individually, but as you look at them, it's really hard to get a sense of what that area actually looks like. What is the kind of the bigger picture? So you can go a step in that direction by stitching these together into a panorama. So now you at least have a little more context, but because you're taking a 360-degree view and you're squashing it down into this flat rectangle, it introduces a lot of distortions that are not obvious if you're not trained to interpret these kind of graphics. For example, on the top frame, that curving white line is actually supposed to be straight in the real world. And on the bottom, there are these two rocks that look about the same size and shape, but the one in the foreground is a pebble and the one in the background is a boulder. And if you're new to looking at these things, it's not obvious that that's what's going on here. And you can train your brain to figure this out and make the translation, but it's yet another hurdle to leap over to get to what you actually want, is just to understand the environment. So this led us to the idea is, okay, what if we could give a scientist a headset that she could put on in her office and then walk out from her desk and seeing Mars all around her, as if she were actually standing next to the rover on the surface of the planet. And in that immersive environment, she could create targets to investigate further or make notes and share the immersive view with her colleagues to discuss the data and hypotheses within the space that they're actually trying to understand. So this led to a number of experiments that eventually led up to OnSight. So this is one of our first attempts. This is using the first generation Oculus Rift. And then we literally took a Vicon motion tracker and duct taped it onto the top of this thing. And then we built what's now a primitive looking reconstruction of an area of Mars. So it allowed the user to stand next to the rover, look around, walk around, and see the environment around the rover in 3D. And then to test the effectiveness of the system, we designed a task. And we invited a group of users from the Mars rover missions into our lab to perform this task. And the task was look at an area of Mars using both a panoramic image from the official planning tools and this immersive system. And in those environments, there were a set of marked targets. And the task was look at the targets and draw an overhead map of where those targets are in relation to the rover. And to get people started, we gave them a start of a map with the rover in the center, and we gave them one marked target. So you had kind of two fixed points of reference, and the task was look at the environment and fill in the rest of the map. We found that using the immersive system, people were more than twice as accurate at estimating distance and more than 3 times as accurate at estimating angle, where angle in this case is a bearing from basically north to where the target is. So here are those two error metrics plotted on a scatter plot. And the X's indicate the performance of the users who used the panoramic image first. And you can see there's a variety of performance. Some people did quite well, and some people did not as well. So here's the performance of the users who tried the immersive system first. And in this case, all of the users showed very strong performance. And I think this is very interesting because only one of these users had worn a head-mounted display before, and they got about a minute to familiarize themselves with the system before starting the task. So I think it's very interesting that even novice users can perform very well when using this sort of system because it taps into the spatial reasoning skills that we develop instinctively as humans and we use every day. This is the way that we're used to looking at the world. So here are some of the maps produced by the subject, or the test participants. These are the maps produced, oh, sorry, I skipped a slide actually. These are the maps produced by the last three participants who used the panoramic image first. And we didn't choose these specially, they're just the last three who did the task. So on the upper row, we have the correct map of the scene. On the lower row, we have the maps produced by the three subjects. And I think you'll agree that they don't really look that similar. So there's some differences in interpretation in the scene. Now, here are the maps produced by those same three participants using the immersive system. And I think you'll find that they're starting to look much more similar to each other and also much more similar to the correct answer. So we would posit that these three people are in a better position to start having a conversation about an area of Mars using a similar understanding of the scene around them. So I'll show one more graph before I move on. Here are all the data points for all of the users plotted on one set of axes, where error in the two dimensions are the axes. The colors indicate the target identifier, and the X is the correct position of that target. So this is using the panoramic image first. And here's using the prototype immersive system. So you can see the variance has gone down a lot using the immersive system. And if we draw a bounding polygon around each of those target areas, you see using the immersive system, there's much less overlap of polygons, and the correct answer is starting to fall closer to the centroid of the polygon. So we're seeing more what we would expect of just natural variation in a sample rather than just fundamental misunderstanding of what we're measuring.
Does that include the training?
No, the way that the people were grouped is they used one system or the other first, and then we kind of measured them based on that. Does that answer your question?
I just think it would get better as they practice more.
I'm sure it would, and that's a great point. And I think that actually speaks to the first chart that I showed, where even using the panoramic image, some people did very well. They did as well as people using the immersive system. So I think that goes to show that most of our users are good at what they do, and that you can train yourself to overcome these limitations. But the technology the immersive technology is a tool that you can use to get yourself there faster with less training. So all of this work and thinking led up to OnSight. So OnSight is an application that we developed in collaboration with Microsoft using the Microsoft HoloLens to put scientists virtually on the surface of Mars. So to let scientists work on Mars from their offices. So this has been in mission operations since summer of 2016. And rather than show you pictures of OnSight or talk about what it is, I'm going to actually do a live demo and give you a little taste of the system. Unfortunately, I did not bring enough headsets for everyone, so this is the best I can do. So in the headset, I'm seeing Mars around me. Now, to share the view with you, we have a virtual camera that's looking at the same environment, kind of from an audience point of view. And I'm trying to navigate to find myself. So I can show both, kind of an audience point of view, looking out from the audience, or I can go to my point of view from the headset. So what you're seeing on screen now is fairly close, minus the sidebar, to what I'm seeing. So as I look around, I see a 3D model of Mars all around me. And I'm here with the Curiosity rover in the Kimberley region of Mars. So we're standing in Gale Crater. So as I look up to the horizon, there's a flat mountain ahead of me. This is Mount Sharp. This is the rover's destination. The rover's actually in the foothills, kind of over that way right now. As I turn, there's a line of distant hills. That's the rim of Gale Crater. So we're in this crater. It's about 100 miles across. And what I'm looking at is a reconstruction of the Martian surface that we've created from images the rover sends back to Earth. So everything you're seeing is real data. And there's no artistic retouching. So this is what Mars actually looks like. And I can bend down, as if I were actually standing on this rock ledge and really see the 3D geometry of this environment. So to create these models, we have a custom photogrammetry pipeline we developed at JPL to take the images that the rover sends back to Earth, stitch those together into a 3D model, and fill in with satellite imagery of Earth where we don't have any images from the rover, because this has very good coverage, but we also do this for where the rover is today, where we may only have a few pictures. So we want to give both the highest resolution view of the environment that we can, and also give context for where we don't have that high resolution data. And that process runs automatically in the cloud as soon as new images are downlinked. So we get downlink once or twice a day, and as soon as those images come down to Earth, we update our models so that our users can launch OnSight on their headset and see where the rover is right now. Sorry. Okay, so let me come back to Earth now. And let's go. Oh, well, thank you. So I want, but before I move on, I want to actually touch on something that Scott brought up. This here is a kind of an artist's conception of OnSight before the application was fully built and deployed. And what we're seeing here is augmented reality, where Mars is everywhere except on the user's computer. So the concept was, let me take my computer with me to Mars so that I can continue using the tools that I normally use, and let me use these two views kind of seamlessly. And we built all of this in an early version of OnSight, where we would detect the user's monitor, cut that out of Mars, and we even had, could drag your mouse cursor off your screen onto the surface of the planet. And it was really magical. Unfortunately, it was also really hard for the users to set up. So we had to kind of put that feature on the back burner in favor of ease of use. But this is kind of what I see as how do these tools talk to each other? Because I don't think you want to have your VR tool and do your VR thing and then go back and do your 2D thing. I'd like to see these streams converging so that data can flow between them more seamlessly. So OnSight was launched in the summer of 2016. We, at this point, have about 50 HoloLens units distributed to members of the MSL science team around the country, also a few in Europe. And we've seen consistent usage through all that time. We get telemetry from the headsets, so we know how much users are using it, what features they're using, and what areas of Mars they're looking at. And during that time, OnSight has received consistent usage and become a widely accepted part of the mission. So OnSight's a great tool for science and engineering, but we also think that this technology has a lot of potential to share the journey to Mars and other remote environments with the world. So we took the core of OnSight and we built an experience called Destination Mars. So we took out the science planning features and we turned it into a museum experience where you can take a group of museum visitors on a guided tour of Mars led by a holographic capture of astronaut Buzz Aldrin. This was installed at Kennedy Space Center Visitor Complex in the summer of 2016. It ran for a pilot program of 3 months and served about 30,000 users. And I think what's really exciting about Destination Mars is that it lets people see the same reconstructions of Mars that our scientists get to see at work. So it's a really cool way of bringing the public along on that journey. But unfortunately, it doesn't scale well because you had to actually go to KSC, to the visitor complex, to see it. So since then, we've been looking at other ways to hit kind of a wider audience. And this past summer, we released an experience called Access Mars, this one in collaboration with Google. And Access Mars is a web VR experience that takes the same train models and takes you on a guided tour of Mars that runs on any modern mobile phone, smartphone, laptop, or VR headset. And so I think I'm about at time here. So I'll just wrap up by saying what OnSight does is show you data that's inherently spatial and let people have a situational awareness and virtual presence in an environment that's hard to visit. Mars is an extreme example of that, but there's a lot of other applications where the same idea can be used to great effect. So with that, I think I'm at time, so thank you very much for your attention.
Thank you very much, Parker. We'll take some questions if there are some from the audience.
Hi, I was wondering if there'd been any thought about combining OnSight with the Mars yard and engineering simulations that go on when a rover's stuck or whatever.
Yeah, that's something we've definitely thought about. We haven't had an opportunity to do it yet. Hopefully, in 2020, so hopefully the next generation of I think it'd be really cool to get similar construction of Mars yard on Earth. That way, the Mars yard is easy because you can also extend that idea to field sites and less environments. We're talking about field missions that are Earth-based that take robots into environments that are difficult to get to. Possible to like or whether it's ice caves through to glaciers. There are a lot of we did a field deployment in Hawaii to support actually searches for Mars analogs in all the fields. We can use these same kind of ideas for virtual presence in Earth-based situations that are Spartan based.
And one question over here. I'd like to just go back to a little bit before lunch. Someone was asking about how can you make this stuff more accessible to people, like what kind of formats can you make it ready for VR? So my question is, how can we get, say, a 3D model mapping of Mars? Like what format is that model in? Can I put it in my planetarium dome? All of that, so.
That's a great question. Test? Okay. That's a great question. I think that right now a lot of these VR applications are kind of data silos. The direction that we're interested in going specifically for Mars is adopting open standards, in particular a spec called 3D tiles for representing terrain content in a way that's hierarchical and easy to render in VR. So we'd like to release our Mars datasets in that format along with the reference implementation of how to interpret and render that format, and hopefully other tools will adopt it as we go forward. So I think data standards and openly accessible software are my recommendation.
Okay, we're out of time. We need to move on. So why don't we have a round of applause for Parker? Thank you very much.